do.
Yeah, you kind of have to convert the joule amount into watts per second.
Oh, yeah, because I was like, because I couldn't convert either of them, and then I tried like, kilowatt hours and joules, and it was like, yeah.
Oh, believe me, I've been racking on that.
Yeah.
I'm
So-
down to the last problem.
Yeah, so this is the formula for entropy, all right? So, it actually ties in pretty well with the problem we just did. So entropy is measured in joules per Kelvin, so it's heat per temperature. But if we look at this heat as flowing, so if we look at it this way, here's our car. Oops. Draw a Dr. Seuss car for you. There's a wheel well, et cetera. And there's energy in the gas tank. The engine is up here doing its power thing, and out comes the exhaust, right? So oxygen comes in, you got your hydrocarbons in the tank, and here comes your CO2, your NOx, your SOx, et cetera, et cetera. So entropy and time are flowing this way. And if you remember, entropy always goes up with time. So what we're looking at is not just the entropy inside a box, like the Maxwell's demon. We're looking at how quickly entropy is being created. So in this case, we're looking at S dot. So change in entropy over the change in time. So again, here goes entropy flowing, time is flowing. The change in entropy with respect to time is S dot equals Q dot over T equals power over time. That's all. So you take the amount of power in the system and divide it by the temperature, and that gives you the entropy flow.
Okay.
Okay? Yeah.
So then in the case of like metabolic consumption though?
Metabolic consumption, if your body is
When
running,
we find out the heat though, you're just trying to say that my body runs at 96.4 or whatever? Like
your body runs at about 100 watts.
100 watts?
Your body runs at about 100 watts, and how do you know that? Well, because you eat 2,000 calories per day. That's 10 megajoules per day. When we run that through, megajoules per second, we get megawatts. Convert that to watts. That comes out to be about 100 watts.
Okay.
So
So that would be the power?
That's the power.
Okay.
You're a 100 watt light bulb. Sometimes more if you're really cruising, 300 watts. If you're Lance Armstrong running on EPO, you might be knocking on 600 watts.
So then that does have to bring into context like the amount of electricity that one light bulb uses.
Yeah.
That's the equivalent of your body. Like
Yeah.
you would have to work really, really hard, like pedaling on a bike or something to power one light bulb.
Yes, you would. We've got, and that's where the whole thing started, was we all have, each North American has about 120 techno slaves running for us. Like if I wanted to be running this laptop, it would be a strain. I'd be up here pedaling away, and I would be a little short of breath, and yeah. You'd be over there, Mariah would be pedaling the projector, and
Meanwhile, we're all pedaling away in the gym and
Yeah.
electricity just goes.
Well,
to
that's-
goes to nothing.
That's where my company name, Human Powered Future, came from. Just even today, I'm like, here, I'm on my bicycle. When I'm coasting, the only energy going in is like my heart beating, and I'm not even doing anything. And gravity is taking care of it. And meanwhile, here comes the 3,000-pound chunk of glass, steel, rubber, running at 20, 30, 40, 200 horsepower, whatever. Not that much, but so the goal is to move yourself, not necessarily to entropicize the planet.
So you take that 100 watts amount and then you divide it by the base temperature of
Yep.
the being?
Well,
In
you
Kelvin?
divide it by, no, you don't divide it by your own temperature, you divide it by the temperature at which you're shedding the power. You divide it by the ambient temperature.
So that's in the
Which
main,
I-
that's in
And you have to do it in Kelvin.
Okay.
You have to do it in Kelvin. So ambient temperature right now is, 305 Kelvin. That'll give you your entropy. Yeah. If you're doing the same work at a lower temperature, you're entropicizing faster.
I guess.
So just divide that 100 watts by the temperature of the atmosphere in Kelvin. That's your answer.
Okay.
Yeah, that's it.
So then, for the other one though, where you're trying to do, like technological.
Yeah.
That's kind of a little harder because you say like, okay, well, I guess like, the number I got was that we consume 55.9 kilowatt hours a day,
Technologically.
technologically.
That's a reasonable number, yeah.
So then we would do that divided by.
Just air temperature.
Just air temperature?
Yeah.
Same thing?
Yeah, same thing,
Okay.
just air temperature. But you have to do the air temperature in Kelvin.
Yeah,
That's critical. You
So
have to
305 Kelvin.
300, just figure out what it is in Fahrenheit, convert that to Kelvin.
Then what should our unit, our end unit be then? Would it just be whatever number watts per Kelvin?
Watts per Kelvin, yeah.
Oh, I get it.
Yeah, watts per Kelvin,
Oh.
yeah. And really what that is, Kat, it's the slope of this curve.
So you're just trying to see what's the rate of entropy production?
That's exactly what you're
That
doing.
makes sense.
Yeah, yeah. Because a lot of times, we say, hey, entropy is increasing, but it's rarely measured, and that's what my 2014 and 2016 paper were trying to get at, is what's the entropy acceleration rate of human civilization beyond the background?
Yeah,
No, that's it.
cool.
Cool. All right, I think, yeah, you're welcome. I'm just gonna bang extraordinarily quickly through the last half of chapter 10. If we were not going to this awards banquet, which would be terrible not to show up for your own party, I would spend more time on it, but we do have to head over there, or I do.
What is this?
I was nominated for the Sustainability Award for the university and
Congratulations.
I think I won. I think I won. Anyway, Nikki Fear, my colleague in climate change studies, nominated me, and Eva Rock, or Eva Rocky, I think is going to give the award. So what we're looking at here is just energy management of a tidal basin. What we're looking at here is, what the next set of technologies look like. We know this is more expensive, but, perhaps lower impact in a lot of ways, higher efficiency, different ways of sending electricity around the world as we become more electrified, as we reinvent fire. Again, the world gets more connected all the time. This gets back to the Solutions Project, showing a few different energy, all renewables and how they tie in with each other. Hydrogen, lots of water around. When you send electricity through water, you get air. Sorry, we're destroying water, but you get you get air in the process. It comes back. It comes back in the reverse stream. And this is just showing when we move to the hydrogen economy ultimately. The hydrogen economy, by the way, is how the entire energy technology program got its start. Paul Williamson had a plan for taking the entire Missoula Valley off the carbon grid. He had hydrogen-powered monorails running back and forth. He got himself crosswise with the former provost. Unfortunately, I don't know, was asked to leave, fired something, whatever. He's in Colorado now. He moves pretty quick, that Paul. But this is the idea for 100% renewables, using hydrogen as a storage medium, as a renewable storage medium, rather than carbon as a non-renewable ancient source, getting back to that 10 million to 1. Phasing out fossil fuels, you can see it's happening to some degree. Gas came online. It'll have its bubble. Just think of that as a big earth burp. Sorry. Oh, excuse me. Pardon me. And others coming online. Some nuclear in there. It's all in energy. Different scenarios, so a lot of different think tanks look at this and how we convert. Here's what it might look like at a city scale, and we're already seeing this. There are Tesla charging stations. There's an electric car charging station downtown at the parking lot there on Main Street. Here's your geothermal. Here's your heat pumps. There's the heat storage system we saw earlier, and this is where we're heading. This is where we're heading. A couple different scenarios. That's the kind of the not so good, business as usual, more aggressive. If you look at the Amory Lovins, you'll see these figures as well. That's at 500 exajoules. I don't know where it stands right now. It looks like it might have peaked in some ways, at least energy per person. That's what Greenpeace thinks we might head. Electricity generation. Again, different organizations doing this type of analysis. And there you have it. Wish we had more time, but I gotta book it. So, thanks everybody. I'll finish up grading. Send me your last summaries, problem sets. I'll knock those out over the weekend. Grades for me are due the Tuesday after finals week. So if you need a lot more time, grades technically are not due for 12 days from today. Yeah.